The aim of this experiment is tracking the motion of an object that is moving at constant velocity using video analysis tools like Tracker, and comparing the experimental data with theoretical data from a computational model by observing plots to discuss how close the real-life example is to theory and to identify sources of error. The physical principles involved in this experiment are the Newton's laws of motion, like Newton's first law and the momentum principle, the general kinematics equation, the position and velocity update formulas, and the iterative computer model for position estimation. When comparing the position versus time plots, it was observed that the best fitting curve for the experimental data is a quadratic curve, whereas the best fitting curve for the theoretical data is a straight line. Thus, there is a change of velocity in real life that is not accounted for in the model. This change of velocity is caused by friction force between the object in motion and the surroundings. For the velocity of the body to remain constant, according to Newton's first law, the net force acting on the body must be zero. Thus, according to Newton's second law, the instantaneous rate of change of velocity is zero. According to the velocity update formula, the velocity remains constant. So, the position can be plotted according to the position update formula. The x-coordinate of the position, the speed, and its instantaneous rate of change will theoretically follow the next trends when plotted against time. For this experiment, I used stickers as distance markers and books as an inclined plane for getting the marble in motion. Also, I used my phone's camera to record the motion of the marble. The distance between each of the markers is 0.02 meters, and the marble was launched from a height of 0.09 meters. In this case, the system is the object in motion, which is a marble, and the surroundings are everything else. The main elements from the surroundings that have an effect on the system are the floor and the earth. At the top of the incline, the forces acting on the system are the normal force, the weight, and friction. They can be expressed with the following equations. Assuming there's no friction, the net force will have an x component, which is the mass times the acceleration of gravity times the sine of theta. Given the following parameters, the initial velocity of the object can be calculated from the velocity update formula as shown. When the marble reaches the bottom of the incline, there is a change in the coordinate system. The origin is placed at the end of the incline plane, and the positive x-coordinates are in the same direction as the direction of motion. We assume that the velocity remains the same and that there is no change in momentum when the object contacts the ground, as the initial velocity for the experiment is as shown. We can use a computer model to simulate the uniform velocity motion. The program estimates the position of the ball through iteration using the position update formula. First, the initial conditions of position and velocity are set. Then the computer is given an initial time and a time step. After that, the net force is inputted. For the first time step, the position is updated by displacement in 0.01 seconds to the initial position using the position update formula. Right after, the model updates the current time, and the computer takes the updated position and adds the displacement in the next 0.01 seconds, updating the position again. As the acceleration is zero, the displacement will be fixed. This process continues until the computer is told to stop. When running the program, the following plots are generated. For the position versus time, we get an increasing line that starts at the origin, whereas for the velocity versus time, we get a constant 1.04 meters per second. In the experiment, the marble was dropped from the top of the incline plane while recording, and the position of each time frame, recorded at 60 frames per second, was annotated using Tracker. For the position versus time plot, we can see that the experimental data are following a linear trend. The slope of the trend is actually constantly decreasing, so the best fitting line is actually the general kinematics equation. Whereas we can see that in the red, the theoretical data will follow a linear trend. While we can see that the theoretical model can actually predict with reasonable accuracy the position in the first instance of motion, then both lines quickly diverge. When plotting the speed versus time, we can see that the theoretical model is a constant value, whilst what we obtain is a decreasing linear trend, which means that there is a net force acting on the body that is trying to stop the body. So it is a restrictive force, and it's the friction that the ground instills on the ball. We can take the derivative of both trends, and we can actually see that whilst in the theoretical model there's no acceleration, in the real scenario there's actually some acceleration, and the acceleration is actually varying, which is probably due to an error. The varying scale in the video due to the recording angle could have generated systematic errors. The following picture showed the same measuring stick placed into different intervals. Hence, the stick was continually modified to try to limit the error. Also, the stickers were big, so the stick could have been slightly unadjusted due to the limited recording resolution, and the marble was small, so sometimes it appeared blurry and was difficult to track. The ground was not completely smooth and had irregularities, which should have accounted for the varying acceleration. It should actually be constant acceleration. Finally, the marble experimented a change in momentum at the bottom of the slope, so the initial speed is not exactly defined. If we flip the x-axis, the magnitudes of the position, speed, and acceleration would remain unchanged, but the vectors would be negative. Hence, the plots would be flipped with respect to the y-axis. For example, the plots for the theoretical scenario would look like this. In the experiment, the net force was not zero. However, if it were zero, it would be possible to tell how many elements from the surroundings are interacting with the system in a significant way. For the net force to be zero, the object would probably have to be in vacuum or free space and not interact with anything, or experience two counteracting forces such as thrust and resistive forces. The main takeaways of the experiment are that, so in this experiment, the object's position was recorded with tracker and its motion was compared to the theoretical model. It is very challenging to obtain a pure or quasi-constant velocity motion by rolling something on the ground. And the model predicts with reasonable accuracy the position of the object in the first few instances, but then the theoretical and experimental plots quickly diverge.